Thank you for the presentation. Before starting, I would like to mention that at this very moment, thousands of colleagues, students, educators, researchers, and workers in general are protesting against the policies of the current Argentine government led by Javier Milei. These policies have defunded education, health, and science in the country to unprecedented levels. I want to send my support from here to the people who are currently enduring the sun and even more so the violent response that the government is using against them with the help of the police forces. Okay, let's start. I will present this talk titled Magnetic Nanoparticles, Effect of Magnetite and Maghemite Content on the Heating Efficiency, in which I am to provide a new perspective on the properties that make iron oxide nanoparticle systems particularly interesting for applications in magnetic hyperthermia. First, I will present some introductory aspects regarding magnetic hyperthermia. Magnetic hyperthermia is a cancer therapy that employs magnetic nanoparticles to generate heat in tumor cells. Generally, iron oxide nanoparticles are used, which when exposed to an alternating magnetic field, they produce heat through energy dissipation, raising the temperature of their surroundings. Back in 2002, Rosenzweig published a study where he breaks down how magnetic nanoparticles interact with these alternating magnetic fields. He came up with a formula to figure out how much power these tiny magnetic particles lose based on the linear response theory. Basically, the power is tied to how long it takes to the particle's magnetic moment, this is their direction, to flip from one stable state to another. And those stable states are determined by the system's anisotropy energy. For practical purposes, these systems are often considered to have an uniaxial anisotropy, defining two possible stable states separated by an energy barrier determined by the product Kv, where K is the anisotropy constant and V is the volume of the nanoparticle. Anisotropy constant is approximated as an effective volumetric energy density that includes a contribution from size, shape, dipolar interactions, and crystalline ordering. In this talk, I will focus particularly on the contribution of the magnetocrystalline anisotropy determined by the nanoparticle's composition. Particularly, the anisotropy is decreased when magnetite nanoparticles are oxidized to Maghemite. This is not always being considered in the design of efficient heat mediators. Next, I briefly describe the main experimental results. We have prepared monodisperse nanoparticles by a thermal decomposition method in organic phase. Mossbauer spectroscopy was key in figuring out the phase composition of magnetite and Maghemite in the samples. Plus, EELS microscopy showed that the particles are totally uniform with no core shell or another kind of hybrid structures. So we can say that the particles made using this synthesis method could be treated as non-stoichiometric magnetite. For biomedical application purposes, it is desired to change the initial coating to an aqueous dispersible one. By doing so, we obtain that for water-transferred nanoparticles, Mossbauer spectroscopy revealed that after a simple ligand exchange process, all samples underwent oxidation, thus modifying the relative magnetite and Maghemite content and thus their magnetic properties. That will affect, indeed, the heat dissipation when thought as a potential magnetic hyperthermia application. Here we see results on saturation magnetization and effective anisotropy as a function of the mean nanoparticle size of the study samples. This includes, of course, results for as prepared in black and fully oxidized samples. We made a process to convert somehow the initial nanoparticles to Maghemite nanoparticles. As it can be seen, the behavior is as expected, with saturation magnetization increasing with particle size and magnetite content. This result reflects also the interplay between the magnetite content that governs the magnetocrystalline anisotropy and the surface anisotropy in the case of the smaller nanoparticles. That is prominent in this case. And the heating efficiency in a liquid medium was evaluated through the specific absorption rate obtained by calorimetric measurements and by using the following equation relating the heating rate, the heat capacity of the dispersive medium, and the nanoparticles fluidic concentration. From this result, it was found that in addition to size, there is a clear dependence of the specific absorption rate on the composition of the nanoparticles. This is evident in this graph, where the peak heating rate shifts towards larger size when the particles undergo oxidation. Okay. So we made a comparison with theoretical results to shed some light on this last result. We made simulation of heating efficiency based on the linear response theory. Our calculations are based on the power dissipation relationship formulated by Rosenzweig, from which two aspects are highlighted: the dependence on nanoparticles composition through magnetic anisotropy and relaxation time. This is the magnetic anisotropy or effective anisotropy of the nanoparticles affects directly on the power dissipation through the relaxation time. And it is good to think about the effect of the size distribution. From this, I mean dissipated power weighted by a nanoparticle radius distribution function is obtained, bringing the problem closer to real system scenario. Basically, we approximate the effect of the composition directly on the value of the effective anisotropy in a straightforward manner by accounting for the individual contribution of magnetite and Maghemite. Similarly, the contribution of saturation magnetization in the equation is also considered. These parameters are introduced to Rosenzweig's formulation based on the value of the volumetric fraction of magnetite. It's this phi parameter that is equal to 1 for magnetite and equal to 0 for Maghemite. The left graph shows the experimental SAR results, specific absorption rate values obtained by calorimetric measurements of liquid dispersion of the presented samples. The results correspond to as prepared samples in black and fully oxidized samples in red. And the graph on the right shows simulation of the specific absorption rate values as a function of the magnetite content. Inside this, it is highlighted the mean size values of the studied samples, two of them from which the two samples that show the higher specific absorption rate values. As it can be seen, this theoretical approach some way confirms the experimental results. As for larger nanoparticles, it is better to for heating performance to obtain Maghemite rich composition, not so in the case of the smaller nanoparticles, in which magnetite rich composition is desired. Here I display some concluding remarks regarding this work. The oxidation degree on iron oxide nanoparticles is closely related with their heating performance in a potential application on magnetic hyperthermia through effective magnetic anisotropy of the system. Larger nanoparticles have better heating performance for Maghemite-rich content. Instead, smaller nanoparticles have a better performance. This will be obtained for magnetite-rich content. Overall, allow me to highlight that this represents somehow a new insight on heating efficiency regarding magnetic hyperthermia. A precise control on the nanoparticles stoichiometry opens a new door to a way for addressing heating efficiency in this kind of systems. Last, I want to acknowledge the NIFTA is my workplace, and some other groups of the Universidad Nacional de La Plata and CONICET Argentina that made some effort to achieve this work. Thank you.
Thank you so much for your talk. We have some time for questions, if anyone would like to ask one for the speaker. I can get us started with that. So you talk about iron oxide and this ability to kind of tune the thermal properties through this oxidation process. Are there any other candidate magnetic particles that would also be considered for this application? And if they are, why is the iron oxide system superior?
Sure. There is a lot of materials. Cobalt ferrite, for example, it's outstanding. It's proved. It was already published that results from other co-workers and among the world that cobalt ferrite, for example, is have outstanding performance in heating efficiency. The key is the effective anisotropy of the system. Cobalt ferrite is known that has a large anisotropy, generates hard magnetic materials, and this will bring more heating efficiency. So for cobalt ferrite core shell structures, for example, we are indeed working working with this kind of materials to generate by some thermal treatments on the material, generate a concentration gradient inside the nanoparticle, not a core shell structure, well-defined core shell, but a gradient of concentration of cobalt ferrite that increase more the anisotropy and we expect the heating efficiency. So
Okay.
there is a lot. The key is the treatment and the tuning of the anisotropy of the system by generating these gradients of concentrations.
Okay, thank you. We have time for one last question. Okay, with that, I would like to thank the speaker. Juan, thank you so much for joining us and for giving